a initial conception of the atmosphere in our environment, the I think quite striking and sadly entrepreneurial perspective that we only have one atmosphere, and that this atmosphere connects to our environment, our water and our soil and our society in really quite complex ways. And if in and that air pollution and climate change are really two deeply interconnected, if in not entirely overlapping issues. And if we look at our planet in that particular way, we can identify certain types of activities that we can change, which can have impacts, multiple impacts, hopefully synergistic and positive impacts over different timescales. And when it came to the focus of the CCAC, what we were attempting to do was to find actions that we could take in our environment, in our economy, and in our society that could achieve both near-term avoided warming and air quality benefits, which would benefit both human society and our ecosystems, biodiversity, and agricultural systems. Those choices led us to a set of actions which focused primarily on mitigating methane and black carbon rich sources of fine particulate matter air pollution, as well as HFCs, because of their relatively short atmospheric lifetimes and their impacts on air pollution. That is where the concept of SLCPs comes from. But it came not from a choice to focus only on those pollutants, but a truly holistic perspective on the environment, and then selecting for a set of actions which achieve a certain set of benefits within a certain period of time. And I point that out because it's very easy looking back to say, hey, N2O, which was the topic of this global N2O assessment, has never been within the remit of the CCAC. And in fact, me being functionally the chief scientist of the CCAC, that's something that I brought up 2 years ago when our board said, "Could you please look at this issue?" I said, that I mean, I appreciate the importance of N2O from a climate perspective, from a biodiversity and ecosystems perspective, but it is by definition neither short-lived nor is it an air pollutant. So it's difficult. It would be difficult for us as a coalition to justify really taking a hard look at nitrous oxide and the myriad of impacts that this particular pollutant has on our ecosystem and our atmosphere. But in truth, it has always been part of the DNA of the CCAC, because we always took a totally holistic look at the environment. We've always just filtered for a set of activities which achieved a certain set of benefits within a near-term time frame. If we take a larger perspective on the impacts and the longer term perspective on the impacts of climate change, and we look beyond just the atmospheric pollutants, and we look at the full system of pollution that is caused by the nitrogen cycle, not just by N2O emissions, but by all of the emissions that come from the nitrogen cycle, then in truth, N2O is fully within the remit of the CCAC. It is in fact the one pollutant that links both. Thank you, Mark. I'll speed up here. Both air pollution, climate change, soil pollution, and water pollution in a way that we have never in the CCAC really engaged with. And that is what's really the most exciting aspect of this assessment for me, is not only are we able to take where we have been really quite effective in the CCAC, both by linking air pollution and climate, but by bringing in all of the other nitrogen pollution aspects, particularly soil and water pollution, to and bring it to our partnership to engage them to take action on this very complex pollutant, and hopefully to drive them to act not just from a nitrogen perspective, but from a climate and air pollution perspective. in the near and the long term. So I'm going to stop now because brevity is not one of my strengths. I'll just keep talking forever. But you guys didn't come here to hear from me. You came here to hear from the lead authors of this report. So Ravi and David, as co-chairs of this assessment, it could not have been done without your incredible, diligent work. Mark and Rona as well. Mark, one final sentence I think I'll make here is that this assessment, we produced it in 8 months. A complete assessment with new scientific and modeling data that could not have been produced if not for the incredible efforts from the entire authorship, but also the contributions and the very gracious contribution of the international nitrogen assessment community. It could not have been done, and I am eternally grateful to all of you for the work that you've done. This is a transformative assessment, and I hope you all, the audience here today, agree with me that the conclusions are impressive and should be taken forward
Thanks
by
very
our
much.
policy.
Yeah, thanks, Nathan. And that's great to set the scene. What we're going to do now is hear from 3 of the speakers. We're going to start with Rona Thompson, who's a senior scientist at the Norwegian Institute of Air Research, an atmospheric modeler interested in atmospheric dynamics. And I'm going to pass straight over to you, Rona, to take us through your part of the story.
Right.
You're muted.
So can everyone hear me and
yes,
see my
thank
screen?
You.
Yeah. Okay.
All
good. Yes. So thank you for the introduction. And I'm going to be talking about nitrous oxide sources and their trends. And this draws a lot from the introductory chapter of the nitrous oxide assessment. So for further reading, I can refer you to the assessment. So we'll start with some key messages. As you all are aware, nitrous oxide is a potent greenhouse gas and presently contributes about 0.1 degrees to global warming compared to the pre-industrial mean temperature. And it's increasing in the atmosphere. It's increased about 20% compared to the pre-industrial value, and it's increasing at an accelerating rate. So the mean growth rate over the last 5 years has been about twice that of the early 2000s. And emissions are increasing globally, and from 2000 to 2020, they've increased by about 1.8 megatons per year. And this has been largely driven by emissions from the agricultural sector. So I'm an atmospheric scientist, so I'm going to start by talking about N2O in the atmosphere. So nitrous oxide is measured in the atmosphere at a lot of sites around the world. Direct measurements began about the 1980s, and prior to that, we can estimate the atmospheric level based on air extracted from firn and ice cores. And that's shown in the top plot here. And you see that pre-industrially, N2O was quite stable at around 275 parts per billion. And then in the 20th century, it started to increase quite rapidly. And this has been related to, of course, the important Haber-Bosch process of producing ammonia and to the widespread use of synthetic fertilizers starting around the middle of the 20th century. So based on the atmospheric level, we can also determine a global source. And the pre-industrial source was about 17 megatons per year, of which only a small fraction was due to human activities. And today, well, in 2020, the global source was about 28 megatons per year, of which 35% is due to human activities. So atmospheric observations are, as I said, made in many locations around the world at the moment. And these measurements are a very good indicator for the trends in nitrous oxide emissions, as well as the distribution of emissions. And using statistical methods and models of atmospheric transport, you can actually estimate the spatially and temporally resolved emissions based on those atmospheric measurements. So we can actually use these measurements to determine quite accurately the global mean nitrous oxide level in the atmosphere. as shown here from 2000 to 2023. And also the annual increase in N2O, or the so-called growth rate. And that's shown here again from 2000 to 2023. And you see that there is also a trend in the growth rate. So each year the increase is getting more and more on average. And in the last 5 years, the growth rate has been almost twice that of the early 2000s. And what more, the growth rate had record levels in 2020 and 2021. So the highest recorded annual increase was in 2020 and 2021. Also, the level of nitrous oxide that we measure in the atmosphere presently exceeds the scenarios used by the IPCC. So these are the shared socioeconomic pathways. These are shown in the figure as the dashed lines. And the observation of nitrous oxide in the atmosphere is shown as the black line. And you see in 2022, for example, the atmospheric level was 336 parts per billion and above even the most pessimistic scenarios. So now I've talked about the atmosphere, I'm going to talk a bit about the global nitrous oxide budget, so the sources and sinks. And these are shown here for the decade 2010 to 2019. The total global source was estimated to be 28.7 megatons of N2O per year. And the total sink is about 21 megatons per year. And the sink is mostly due to atmospheric chemistry occurring in the stratosphere, where you have photolysis of nitrous oxide, as well as reaction of nitrous oxide with high energy oxygen radicals. And the total anthropogenic source in this decade was just over 10 megatons of N2O. The anthropogenic sources are shown in blue, and the natural sources are shown in green. And the natural source was 18.5 megatons. So of the anthropogenic sources, the largest single sector contributing is direct emissions from agriculture, which was 5.7 megatons per year, and then followed by industry and fossil fuel emissions. And natural sources, the most important natural source is that from natural soils, and is also quite a significant source from the ocean as well. So I just want to point out to you that on the very left-hand side of this figure, you see a small arrow for climate change effect, and that's a positive effect due to warming temperatures. So largely warming soils is increasing the nitrous oxide emission, and this has been offset more or less by the CO2 fertilization effect. So between 1980s and the 2010s, there's been quite a significant change, both in the absolute emission per sector, but also in their contribution to the total emissions. So direct soil emissions have increased the most in absolute terms by 67%. They've increased the most in absolute terms, but have also increased by 67%. And they've also increased in terms of their share of the total emissions. Waste has more than doubled from the 1980s and increased its share of the emissions from about 2% to 5%. Indirect emissions have also increased as well as industry and emissions from manure, which have increased by about 10% each. And what's more, aquaculture has emerged as a small but growing source, and in the decade 2010 to 2019 was about 1.7% of the total emissions. So the trend in anthropogenic emissions is about 1% per year on average from 1980 to 2020. And the agricultural emission trend is being largely driven by emissions from the agricultural sector. And you see here the breakdown, and here's direct emissions, indirect, and other, which other includes industrial and emissions from waste, as well as as well as emissions from combustion of fossil fuels. And the total here is shown as the black line. And you see the total is a little bit below the sum of the direct, indirect, and other. And that's because of these so-called perturbation fluxes, which are shown in blue. And these perturbation fluxes have a net, so negative effect. And these are due to climate change, so the warming of soils, which increases the N2O emission. That's offset by the CO2 fertilization effect, but there's also a negative effect on N2O emissions due to land cover change. And I show on the right-hand panel here the uncertainty, so the mean and the uncertainty range for 1980 to 2020. So in each of these estimates, there is still some considerable uncertainty. So we talked about global trends, but there are also different regional patterns. So emissions are increasing in quite a number of regions of the world, in particular in East Asia, in Central and South America, South Asia, as well as to some extent in Africa, whereas they've remained nearly constant in North America, and they've even decreased in Europe. Talk a little bit about the trends in Europe. The emissions have actually decreased by around 39% from 1980 to 2020. And this has been largely due to decreases in non-agricultural emissions. So this is mostly due to the emissions abatement from nitric and adipic acid plants. And this has contributed about 0.5 megatons to the total reduction. There's also been a small decrease in agricultural emissions from the late 80s to around the early 2000s. And it's leveled off, the source has leveled off since then. And actually this decrease in agricultural emissions was not so much due to policies to target nitrous oxide emissions, but rather as a side effect of policies to reduce nitrogen pollution. I want to show just, in the interest of time, just one other region, which is in contrast to Europe. So in East Asia, emissions have increased by more than 100% from 1980. And that's been largely driven by agricultural emissions. And there's also been increases in industrial emissions, fossil fuel combustion and waste emissions, as well as in indirect emissions. What we can see is that for agricultural emissions, these increased up to about 2016, and there appears to be a small decrease since then. So maybe the peak in at least agricultural emissions in East Asia may have been reached. So just to conclude, nitrous oxide is growing in the atmosphere and at a faster rate now than in the early 2000s. And it's even growing faster than predicted by the most pessimistic scenarios of the IPCC. From the 1980s to the 2010s, largest increases were seen in emissions from direct soils, so from soils, from the indirect emissions, and also from waste. And most regions of the world had increasing emissions from 1980 to 2020. But a notable exception is Europe, where the emissions actually decreased by about 39%. And what else we can say is that agriculture has emerged as a small but growing source. And I think it's a source also to keep an eye on in the future. And currently it contributes only 2%, but as I said, this estimate is quite uncertain, and it also appears to be growing quite rapidly. Okay. So thank you for your attention, and that's all from me.
Yeah, thanks very much, Rona. And just to say, we're going to have questions after the speakers, and somewhere at the top of your screen, you should be able to see a Q&A button. So please do stick your questions under the Q&A. Feel free to do that now, and we'll collect them up when it's time for the discussion. So with that, I'm going to introduce Professor A.R. Ravi Shankara, Ravi, to his friends, to all of us, I think, who's a professor in the Colorado State University of Chemistry and Atmospheric Science, and whose work focuses on ozone layer depletion, climate, and urban air pollution. So with that, Ravi, lead you to share your story.
Thank you very much. Venjuru, unfortunately I can't see the slides, but I assume all of you can see it. So
we can see it and we can hear.
Perfect, thank you. The first, let me go to the first slide, please, which says N2O is a greenhouse gas. It is there, okay. All I want to make a point, all I want to show here is that nitrous oxide absorbs outgoing infrared radiation. If you're curious where it absorbs, I've shown you those on the plot on the left-hand side. And it absorbs partly in the window region, so that's one of the reasons it's a potent greenhouse gas. The second reason it's a potent greenhouse gas is it has an atmospheric lifetime of approximately 120 years, so it's pretty long-lived, almost like CO2. CO2 is not as well-defined lifetime, but is similar to N2O. And when you consider these factors, you come up with a global warming potential of a 100-year time horizon of 270. That means it is 270 times more potent than CO2. And it is right now the third most important anthropogenic greenhouse gas after carbon dioxide and methane. Could I go to the next slide, please? All I want to start here is that if you were to reduce N2O emissions, there are other emissions that would also be affected, specifically ammonia, methane, and nitrogen oxides. This slide is kind of busy, but I don't want you to delve deep into it. All I would like you to know is there are some agents that lead to cooling, some agents that lead to warming, some parts that the nitrous oxide that reaches the stratosphere leads to ozone layer depletion, and whatever gets into the water bodies affects water quality. And the fact that you can change the PM and ozone at the surface leads to air quality effects. So there are three key issues that N2O impacts: climate change, ozone layer depletion, and air quality. So N2O is something that you should think about for those three reasons, in addition to water quality and various other things. Can I see the next slide, please? So in the near term, actually reducing nitrous oxide emissions by the measures that you can do warms the planet, but it cools towards the end of the this century. The reason for that is very simple. N2O is a greenhouse gas that would warm, but when you reduce N2O emissions, as you can see on the right, it reduces the aerosols that are produced from ammonia and nitrogen oxides. So the net effect is actually smaller than what the contribution would be from N2O emissions as greenhouse gas itself. But that emission of aerosols that can be sustained for a long time, because aerosols live in the atmosphere only for a few weeks as opposed to N2O. So at a certain point, it turns around and you do gain in climate. This is very reminiscent of how things work with fossil fuel, specifically coal, which had high sulfur content. And there the aerosols also masked the full effect of the greenhouse gases. So if you include methane in the near term along with nitrous oxide, you see the benefits for climate even sooner. But the key point is the net long term is it is going to lead to cooling of the planet, or I should say less warming of the planet. Can I go to the next slide, please? I don't really want you to focus on the left-hand side of this. All I want to say is this picture on the right, that the aerosols, which we think about for climate as climate forcing agents, also are thought of as particulate matter, and that directly affects human health. So if you look at what happens with the nitrous oxide emission mitigation strategies, you do see a very consistent pattern in decreases in aerosols and decreases in surface ozone, both of which then lead to health effects. So could we go to the next slide, please? What this shows is the health effects from cleaner air that you would obtain by taking action on nitrous oxide. The left-hand side shows the cumulative premature deaths in millions on the left-hand side. So as each year goes, it keeps adding up. So you can see by 2050, it roughly is about 13 million deaths per year avoided. I'm sorry, total. And then you can see the same thing for the PM on the right-hand side. There are two different colors in there. One that includes technical reductions and societal changes, and the blue one is only technical reduction scenarios. So these benefits would be tremendous in terms of air quality. Can I go to the next slide, please? So if you look at nitrous oxide, you might wonder, why is it not in the Montreal Protocol if it's an ozone depleting gas? The ozone depleting potential of nitrous oxide has been calculated, and it's about 0.017. That means it's only about 2% of CFC11. But if you look at other ozone depleting substances that have been banned, you can see this is in the same ballpark. But the point is, it is not just the amount, the ODP, but it's the total amount that would happen. If you can give a click, you'll see that essentially, if you connect these dots, you see that N2O is indeed an ozone depleting gas. Can you give another click, please? So essentially, it shows that N2O is considered to be an ODS, or it should be considered an ODS, and something for the Montreal Protocol to take action. In the next slide, you should see the ODP-weighted emissions of N2O. What you can tell, again, is that it's not just the ODP that matters, it is the ODP-weighted emissions. It's just like, it's not just the GWP that matters, it's the GWP-weighted emissions that matter. And even back in 1987, on the left-hand panel, it shows that N2O was a very significant ozone-depleting gas emission, and that is when the Montreal Protocol was signed. And now, of course, it is the most important ozone-depleting gas emission. In fact, it equals the sum of all the other ozone-depleting gas emissions today. And of course, it's larger, and it will continue to grow. This is only the anthropogenic emissions. It is not natural emissions. We're talking about only anthropogenic emissions. Could I go to the next slide, please? And you can see the benefit of this in a few different ways. Here we have exemplified it using a very simple measure. For example, the Montreal Protocol did phase out HCFCs, and the blue line on the right-hand side shows you the benefit of phasing out HCFCs. And the green and the orange line show the benefit of what would happen if you took certain action on N2O. And clearly, the benefits to ozone layer by N2O action is more than the gains made by HCFC phase out. Can I go to the next slide, please? This is something that was somewhat of an unusual, unexpected result in the process of doing this assessment. What this shows is the ozone layer depletion as a function of latitude, and the black line essentially shows the peak ozone depletion due to ozone depleting substances. Most of it occurred at high latitudes. What N2O does, along with methane, is it depletes ozone layer in the 30 degrees north to 30 degrees south, which is where most of the people live. So in terms of the consequence, more people are going to feel the effect of ozone layer depletion by N2O than what people felt from the CFCs in the past. Can I go to the next slide, please? We can convert these into metrics that people think about, such as cataracts and cancers. The right-hand side shows you how it changes in terms of latitude for different kinds of conditions. For different kinds of cancers and cataracts. And the bottom line is the human health impact of unabated N2O emissions could be very significant due to increased levels of harmful UV. And unabated N2O emissions could increase cataract by 1% and certain kinds of skin cancer by 10%. We can't convert it to numbers because we don't have the baseline data of how many cancers are occurring in different regions right now. But remember that cancer and cataracts are useful metrics. There are other consequences of ozone layer depletion. If you go to the next slide, that kind of summarizes what I wanted to say. Most climate benefits would be realized towards the end of the 21st century, and mitigation of N2O could avoid the equivalent of 6 years of current CO2 emissions. I didn't show that in the slides, but I'm just asserting it from the assessment. N2O emission mitigation using current available technologies could prevent 20 million premature deaths by 2050. That's a very significant number. This all occurs because of improved air quality. The ODP-weighted N2O emissions equal all other current emissions of ODSs combined. And ambitious N2O abatement relative to 2020 levels could deliver more than 5 times the ozone benefits of accelerated HCFC phase out, and I already just showed you the effects on skin cancer and cataracts. The last thing I want to emphasize is right now the climate policy is focusing a lot on CO2 and methane. The thing we want to assert is that if CO2 and methane are mitigated, but not N2O, there'll be increased risk of cancer and inability to meet the Paris targets on climate. And that's a very important thing to remember. With that, I thank you for your attention.
Thank you so much, Ravi. And indeed, just a reminder, if anybody's just joined, please do put your questions to Ravi and the others in the Q&A box. Click that and add in your question. We'll come back to you shortly. So with that, let's move on to Professor David Kant, who's Associate Professor in New York University, particularly interested in nitrogen policy development. He's a member of the International Nitrogen Management System work, and as part of this report, been with Ravi, one of the co-chairs of the Nitrous Oxide Assessment. So with that, David, over to you.
Thank you. And Mark, can you see my screen?
Yes, and we can hear you. Thank you.
Great. Thank you. Thank you, everyone. And good morning, good afternoon, good evening. Thank you so much for joining this webinar on this assessment. We're really proud of it and how much we were able to achieve in such a short amount of time. Just to summarize the key points of what I'm going to talk about. So we've heard from Rona and Ravi in terms of the sources and budgets of N2O and the threats that they pose, that it poses not just a climate no zone, but as part of the broader nitrogen cycle and broader nitrogen pollution. I'm focusing on abatement and governance options. And so just for the key takeaways here in the next few minutes is there are technically feasible and cost-effective abatement options for nitrous oxide across all major polluting sectors. Now, as Rona pointed out, there is no ambitious nitrous oxide abatement without dealing with agriculture. That being said, there are some low-hanging fruit, which tend to be non-agricultural sources of N2O, notably industrial nitrous oxide, nitric and adipic acid production. There are cost-effective, existing, technically feasible technologies that are already deployed in many different nitric and adipic production facilities around the world that could reduce emissions over 99%. There are also recent estimates of the social cost of nitrous oxide, the damage that it causes not just to the environment, but to society in terms of increased healthcare costs and other impacts. And those costs make the case for action even more compelling when you compare it to the cost of abatement. And then finally, nitrous oxide, but also because it is such a central component of the nitrogen cycle or cascade, means that there are actually multiple options, multiple fora within the international environmental landscape that are available for addressing it. So to evaluate the abatement potential of nitrous oxide, we leaned heavily on new nitrogen scenarios that were developed for the International Nitrogen Assessment, which is going to be released next year. And what we saw from our assessment, was that compared to 2020 emissions on the left-hand side here, if we follow the most ambitious mitigation scenario, which is a combination of essentially all available mitigation practices, both technologies and behavioral changes, but then also broader societal transformation, especially with the move towards less animal protein consumption, that you can reduce emissions by approximately 40% by 2050 and close to 60% by the end of the century if you do even more fundamental transformations to our food system. Breaking this down, this is in all sectors, but just focusing on the two that I mentioned in the beginning here. Agriculture, again, you can see that we estimate we can reduce emissions over 40% by 2050 below 2020 levels. And for adipic and nitric acid production, that can get close to 90 or 95% abatement because of the mitigation technologies that are already deployed in many places around the world. You will see more examples of these. This is just an example of the table where we just list some of the abatement measures that exist across different sectors. Again, just to emphasize here, and I should say there's a whole chapter on this in the upcoming International Nitrogen Assessment next year. We're focusing here really on N2O, of course. There are these technically feasible abatement measures across all sectors. Again, industrial N2O offers a low-hanging fruit. We estimate that it has an abatement potential of up to 2.5 billion tons of CO2 equivalents and 160,000 ODP or ozone depletion potential tons by 2050. Obviously, agriculture is the elephant in the room in the sense that ambitious N2O action is impossible without it. Now, just a point on agriculture here, and this is something that we raise in the assessment. There are many different abatement technologies and practices that already exist to reduce emissions from nitrous oxide. Some are focused on essentially making the current systems of production more efficient. That's obviously important. Nitrogen, as many of you know, is often referred to as a leaky pipe. From the moment in which we produce fertilizer to the moment that it's actually consumed by us, there are a lot of nitrogen losses throughout the system and throughout the cycle. And so there are ways to try and make this linear system more efficient, but also given, and this is very much in line with both INMS focus and UNEP focus on circular economy, that a move to a more circular economy where instead of nitrogen being in this linear fashion, much of it wasted, trying to recycle, reduce and reuse a lot of the nitrogen that would otherwise be lost to the environment, whether it be about reusing manure, more of manure as a nutrient, whether it be reintegrating crop and livestock production, looking for other sources of nitrogen production, whether it be through green ammonia, on-farm green ammonia production or otherwise. But there are these more transformative actions that can also be taken, that will need to be taken if we are serious about really ambitious action on nitrous oxide. When it comes to the social cost of nitrous oxide, again, these social costs have to do with the amount of damage that is estimated that 1 ton of N2O causes to society. And we've broken it down here in terms of dollars per ton of N2O and then translate that to dollars per ton of CO2 equivalent. And we've compared different estimates of the social cost. From a climate perspective, it ranges from $90 to $220 per ton. And from ozone damages, this should be per ODP ton, but here it's somewhere between $20 to $80 per ton. Now, for some reason, there's another slide of mine that isn't showing up here, but essentially, we look at one example in China, for example, where the average abatement cost across all sectors is around $80 per ton. And so when you compare $80 per ton and you actually sum up the average of the climate and ozone here, you're looking at about a social cost of N2O of over $200 on average per ton of N2O. And so the social benefits of addressing N2O vastly outweigh many of the abatement costs, and definitely the average abatement cost for N2O, making those, and that's not even taking into account the fact that actually much of the environmental and social benefit of addressing N2O comes from avoided other forms of nitrogen pollution, notably to air with ammonia and NOx, as Ravi was pointing out, and nitrate leaching, and then other impacts on biodiversity and ecosystems. Now, because nitrous oxide is both a greenhouse gas and an ozone-depleting substance, there are specific avenues for better governance of N2O, both under the Paris Climate Agreement, that's made up primarily of these nationally determined contributions or national climate action plans. And there has been work both from the CCAC and others calling for more specific and ambitious targets on nitrous oxide under those NDCs. Similarly, the Montreal Protocol, as Ravi was pointing out, the Montreal Protocol has not taken on nitrous oxide, but it could, given that it is the largest remaining threat to the ozone layer, could do that either from just industrial sources, given that that is where the low-hanging fruit is, or it could consider doing it across all sectors. It is, after all, one of the only international environmental agreements that's dealt successfully with addressing an environmental pollution problem from agriculture, notably methyl bromide. Now, as I mentioned, and as we've seen throughout the presentations today, because of N2O's link to the broader nitrogen cascade, it expands available options. Under the new Global Biodiversity Framework, Target 7 calls for halving nutrient losses to the environment. There have been 2 UNEA resolutions calling for more international actions and coordination on nitrogen pollution. And there's an upcoming UNEA meeting next year where there may well be at least negotiations towards the 3rd nitrogen resolution. And the Air Pollution Convention under the UN Economic Convention for Europe is increasingly focused on integrated nitrogen management. So just to summarize here then, there are technically feasible, cost-effective N2O abatement measures. And while agriculture is central, industrial N2O is a low-hanging fruit. The new estimates of N2O social costs make case for action even more compelling, and there are multiple governance options to address it, given its unique chemistry. And then taking an even broader step back in terms of the key messages of the assessment, as was mentioned, nitrous oxide is the 3rd most important greenhouse gas, the most significant ozone-depleting substance currently emitted to the atmosphere. Most emissions come from agriculture, but there are these low-hanging fruit from industrial emissions. And to summarize some of the key points that Ravi and Rona made, the assessment estimates that we can get about a 40% reduction in anthropogenic emissions by 2050. That would avoid the equivalent of over 6 years of current CO2 emissions from burning fossil fuels. It would generate 5 times the ozone benefits that were generated by the last big ozone action taken by the Montreal Protocol. And because of nitrogen's unique chemistry and the links to air quality, here we didn't even have the time to look at water quality and others, which will be evaluated thoroughly in the International Nitrogen Assessment. But already in this assessment, we estimate that you could avoid 20 million premature deaths through improved air quality by 2050. And with that, happy to take all your questions. Thank you very much.
Thank you, David. So let's get all our panelists back with your cameras on. And I already see we have a question for Rona from Joshua Golovati, who asks, he thanks you for the presentation, and how can you explain the fast increase on Africa? So just remind us about those trends and explain the Africa story that Joshua is picking up on.
Right. Yes. Thanks for the question. And so in Africa, we do see increases in agricultural emissions from some large countries. Not all countries show an increase, obviously, but there are some countries, large countries of large populations, where we have seen quite significant increases due to agricultural emissions.
Okay, so agriculture is driving that increase in Africa, is what you're saying?
So other sectors like industry and fossil fuel combustion have been relatively stable, but yeah, our estimates show really this is due to increases in agricultural emissions.
Okay, there's an interesting comment there in the light of African Union's declaration to, I think, triple the amount of fertilizers used in Africa. Does anybody want to comment on what that might mean for N2O? Is that a David point? So if that goal of tripling fertilizer increase into Africa was to be achieved, what would that mean for N2O?
Well, it really depends on how that nitrogen is managed, right? And so there's been a big push to try and, it's similar to the energy story, where we're trying to ensure that much of the global south avoids the same development trajectory that much of the global north pursued in terms of relying heavily on fossil fuels, and then very slowly now transitioning to renewables and other forms of low carbon energy. We hope that while obviously there is a desperate need to increase the amount of access to nitrogen and other nutrients, especially in parts of Africa, that can be done in a way, and there are ways for that to be done that have been tried and tested in every part of the world, for it to be done in a way that avoids the same trajectory that we've seen in other industrial agricultural systems, and that's what's absolutely necessary.
Okay, yeah, thanks, David. So let's, there's another question in the chat here from Nazatul, and it's about the relationship to changing weather patterns, increasing rainfall and drought on N2O emissions, and how should mitigation strategies be adjusted in the light of those climate changes? And I'm not going to see which one of you would like to address that, but I want to roll into that something that you said, Rona, about a CO2 fertilization effect, and that wasn't exactly clear what you meant by that. So maybe you want to start in answering this question, and if you can also roll in the, what do you mean by a CO2 fertilization effect for N2O?
Yeah, so the CO2 fertilization effect means that as CO2 has increased considerably in the atmosphere, and because of that, plant stomata don't have to open as much to take up the CO2 as they would in a lower CO2 concentration atmosphere, and thus they lose less water to the atmosphere. And so they become more water efficient due to the higher CO2. And through that water efficiency, they actually increases their possibility or potential to grow. And with that, also their uptake of nutrients like nitrogen. So through the CO2 fertilization effect, plant growth potentially can increase. And as growth increases, it takes up more nitrogen nutrients. And so there is less reactive or nitrogen in the soils that can escape as nitrous oxide to the atmosphere. So that's essentially what this effect is. Yeah.
And does one of the others want to answer the point about what does it mean about changing rainfall and weather patterns? Ravi, go for it.
Okay.
Thank you. Thank you for the question. It actually, I'll urge you to look at our report and specifically look at figure 4.2. The changes in precipitation patterns are somewhat complex. So you can see where the changes are. There are some places where rainfall increases, some places where the rainfall decreases. So it's a very complicated question as to how climate change induced by nitrous oxide is going to affect the weather patterns. So I really urge you to take a look at the assessment and specifically at figure 4.2 and its description. Thank you.
Yeah, and this question seems to be linked to a question from Anchor Quast on climate change, how that may be affecting N2O emissions from agriculture. Just can one of you put this into a sentence? Essentially, that means that a warmer world means more N2O emissions, or am I simplifying too much? David, I think you're going to react here.
All else being equal, it is true that, I mean, a lot of the drivers of N2O emissions, especially in agriculture, will be exacerbated by climate change. So, you know, increased soil temperature increases biological activity, which increases N2O emissions, especially increased rainfall where there are wetter places, which means less oxygen-rich environments. That also is perfect conditions for N2O. N2O, especially from soils, is very much hot spots and hot moments. So there are these pulses of N2O emissions. So yes, all else being equal, if we were to keep the amount of nitrogen we apply today constant and just see a warming climate, then we would still expect to see increases in N2O emissions.
Okay. And there's a question here from Lamar on the emissions from drained peatlands. Has that been considered as part of the assessment, and how significant is that? Who wants to take this one about drained peatlands?
I mean, it's a very important source of N2O. Again, for this particular assessment, we were relying on emissions projections, these scenarios that were developed for the International Nitrogen Assessment. And so the level of granular detail there was dependent on those scenarios, but that I believe some of those elements will be dealt with in the International Nitrogen Assessment. And the important broader point that I would want to make here, and it's also related to a couple of questions about effective interventions, and we talk about those in the assessment. This assessment, along with the International Nitrogen Assessment, should really be seen as the starting gun for more serious, high-level scientific assessment work to be able to drive effective policy on N2O and nitrogen pollution writ large. And so you're going to need more assessments looking at regionally specific or climate and crop specific interventions that are the most effective, right? This is not the end. This is just the beginning of the science policy interface here on nitrous oxide and nitrogen.
Yeah, thank you. And I want to come back to something Ravi said in your presentations. You were showing some really interesting graphs, Ravi, about the decrease of ozone in different latitudes and how the CFC and so different effect previously was the ozone hole in Antarctica, and you could really see that big depletion in those very south latitudes, but you've got a much smaller spread effect, and then you translated it into some cancer responses. And I guess my question is, would a 5% depletion in ozone mean 5% of the adverse effect? Is it linear or is it non-linear? So, for example, I could imagine that if I was living in Antarctica, a 50% effect of loss of ozone is really going to be a big issue, a big threat. But there's more people affected in the equator because there's more people there. But is a 5% linear or non-linear?
The first part is the linearity question. You're right. When you deplete the ozone by a certain fraction, 5%, the UV change is not just 5%, it's actually larger. So it's an amplification factor. There's a significant amplification factor. And the effect of those changes in UV, that biological amplification factor is dependent on various different issues. Cataracts is not as sensitive, skin cancer is. So again, there's non-linearity in all of those issues. The key point I want to emphasize, like you said, Mark, is we are showing from this assessment there could be significant ozone layer depletion in the tropical and in the region 30 degrees to 30 south 30 north, which is where most of the people live. That was contrary to what happened with the CFCs. CFCs did not change the ozone layer. It didn't cause much ozone layer depletion in this particular region. But this is the region where most people live, most food is grown, so this could be a bigger issue than we thought. We need to look into it more.
Okay, and there's a few questions here about mitigation. One from Patrick Heffer about what would be the most effective mitigation strategies, ones which are also consistent with food security. Is that a question for David? I'm not sure.
Sure. I mean, we could. This is a subject for a whole other webinar as well. The point is, again, what we find in this assessment, what will be highlighted in the International Nitrogen Assessment, is that there are many effective interventions in agriculture that not only can reduce N2O and nitrogen pollution without threatening food security, but in fact make food production more resilient to many of the environmental changes that we expect. And so that's, again, with the caveat being that different interventions will work differently or be different levels of effectiveness in different systems and will work differently with different agricultural practices. But everything from enhanced efficiency fertilizers, so nitrification inhibitors, controlled release fertilizers, to changes in practices of using existing fertilizers more efficiently. So whether that be transitioning from applying in the fall to the spring or splitting up fertilizer application into smaller doses over the growing season, all of those kinds of practices are going to be necessary. And when we, the question of what is effective, well, that will be not just a question of what is environmentally effective, but what actually works in terms of durable, long-lasting farmer adoption. What will be the learning costs and the additional labor costs and the additional financial costs, obviously, of adopting these technologies, and what policy interventions can be made to try and lower those barriers to adoption. That will be the absolute.
Thank you. Thank you very much, David. Well, we've come to 1400 and we're running out of time. I see lots more questions in the chat, but I'm afraid it's going to be impossible to take them all today. But do follow up with our experts. I'm going to thank Nathan particularly for hosting this from the Climate and Clean Air Coalition, with which INOS has partnered, and I as our great network. And I'm going to pass over now very quickly to Ning Liu, our Secretariat in UNEP in Nairobi, to close our session. And thanks everybody for joining us. To you, Ning.
Okay, thank you very much, Mark. Dear colleagues, on behalf of the Secretariat of the Global Partnership on Nutrients Management, I extend our sincere appreciation to Dr. Rona Thompson, Professor Ravi Shankara, and Professor David Kanter for sharing your invaluable insights on nitrous oxide assessment. We also deeply thank our colleague Nathan and also Professor Mark Sutton for their support in co-organizing this webinar alongside the International Nitrogen Initiative. Nitrous oxide is addressed by several international environmental agreements, including the Paris Climate Agreement and the Vienna Convention for the Protection of Ozone Layer. Parties to these agreements could consider more focused actions to tackle the challenges posed by the nitrous oxide. The successful approach of the Montreal Protocol in managing byproducts emission could serve a model for addressing nitrous oxide emissions. Furthermore, the two resolutions on sustainable nitrogen management were adopted by the United Nations Environmental Assembly, UNEA, in 2019 and 2022. A UNEP working group was established in 2020. To date, 96 member states have nominated focal points to this working group, which is assisting countries in developing national action plan on nitrogen management. It is our hope that nitrous oxide emission will be addressed in these action plans. It is worth noting that Target 7 of Kunming and Montreal Global Biodiversity Framework calls for countries to halve nitrogen pollution by 2030. Implementing a sustainable nitrogen approach could significantly strengthen the achievement of several sustainable development goals. The Global Partnership on Nutrients Management remains committed to collaborating with scientists, policymakers, the private sectors, and NGOs to raise awareness of nutrients pollution and explore solutions to address these challenges. Thank you very much for attending this webinar. We look forward to attending our future webinars. Thank you very much. Then we close this webinar. Thank you.
Thank you so much, Ning. And just to say, if you haven't yet looked at the report, please do Google or whatever search you prefer, the Global Nitrous Oxide Assessment and the Climate and Clean Air Coalition. And as Ravi says, there's lots of information to be looked at there. Thank you, everybody.
See you.
Thank you. Bye-bye.
Bye, guys. It was fun.